let's get where we were here. Too far. I think this is what we were ready for, actually. Yep, right after the temperature conversions. All right, so we're going to talk about gas characteristics, and again, we've already kind of done a lab over this, but this will help explain the lab. I don't know why this guy represents gases, but he's got a long face, so I guess I kind of like him. And then I don't know, think of weird things, like someone coming up to this guy and going, "Hey, buddy, why the long face?" And it's because he's, but you don't mean that. And I don't know. Anyway, moving on. Usually people say that. Maybe you don't know that expression. Never mind. Okay. Yeah, because it's sad. This guy's not sad. His face is just long. The characteristics of gases, the ones that we're going to talk about here: volume, amount in moles, and we're going to specifically talk about moles. Now, you can talk about amount in, sometimes this might be given to you in grams, and then you'd have to convert it to moles, okay? But we can do that, right? What do you use to convert from grams to moles? Dimensional analysis using the molar mass on the periodic table, right? Okay. Pressure and temperature, okay? Now, you need to hear me on this. This is very, 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 very important. Okay, that's why there's lots of exclamation points here. When you do gas law problems, from here on out, when you do a problem in this class, your temperature needs to be in Kelvin when you're doing, plugging it into any of these gas law equations that we learn, okay? Temperature has to be in Kelvin, okay? So really, the only time in this unit when your temperature would not be in Kelvin is if I specifically ask you to convert a temperature into Celsius or Fahrenheit, okay? Like the temperature conversions we did at the end of last week. So anytime that you have one of these gas law problems, you need to convert to Kelvin. That's why I wanted you to memorize that 273 number, because you're going to have to be doing that conversion a lot, all right? Okay, so Boyle's law. There's Robert Boyle. Yep, that's the guy. That's what guys looked like back then in the 1600s. So Boyle's law is the one that relates volume and pressure, okay? And we're just as great as Boyle because we came up with this law on our own, didn't we?
Yeah.
What's the relationship between pressure and volume? Okay, so if the pressure increases, that's going to cause a decrease in volume. In other words, they're inversely related. And that's what Boyle realized, not probably by putting one of these together, but by doing a lot of complicated tests, okay? So now you guys are as smart as Boyle. I'm not sure that your hair is as great, but you're as smart as him. So for this law to work, you have to hold two things constant. The number of moles of gas has to be constant, and the temperature needs to be constant. Now, in our Cartesian diver experiment, is the number of moles of gas constant here? In other words, are we losing any gas out of this tube, or are we gaining any gas into this tube? Probably not. I mean, for the most part, now there might be a few bubbles out here that bubble up into there every once in a while, but for the most part, this gas can't leave and new gas can't come in, all right? So we're holding the number of moles constant. And the temperature in this room is not really changing drastically over any given time, okay? So moles and temperature are constant here. If the pressure increases, the volume would decrease, and vice versa. If the pressure decreases, the volume would increase. I wish I had one of these to show to you. I had one at my last school, and it's kind of fun. It's a little vacuum chamber. But if you can, and basically you just had a little pump, and you could pump all the air out of it, or a lot of the air out of it. So what I used to do is put a marshmallow into the vacuum chamber. You pump the air out of that thing, and the marshmallow just gets huge, because all the air in the marshmallow starts to expand, right? And then it's fun, because when you take the cover off of it and let the pressure back in, a lot of that air has escaped out of the marshmallow, so it just shrinks down to a tiny little marshmallow, okay? It's fun. I wish I could show it to you, but we don't have one of those vacuum chambers here. All right, so the equation for Boyle's law. Sorry, it's way down here at the bottom. That might be hard to see. Oh, you've already got it on your paper, so you don't have to worry about it. P1 V1 equals P2 V2. Okay? What does that mean? Okay, so basically we're talking about changing our pressure and volume conditions, right? So if you've got an initial pressure, pressure 1, and an initial volume, volume 1, and then somehow you change the pressure, which is what we did in this, right? We changed the pressure by squeezing the bottle. Now you've got pressure 2, and then you're figuring out what's your new volume at that pressure, okay? All right, so here's, whew, really kind of zipped in there, didn't it? So here's a problem using Boyle's law. Well, not yet. I guess you have a couple more things to fill out here. But all of this is filled out for you, so let me just put this up here and talk about it quickly, and then we'll get to some actual problems. But if you know that the temperatures in moles are constant, then you can do this calculation, okay? These problems are going to contain 3 numbers. 2 of them might be pressures, the other one might be a volume. Okay, then you're solving for the second volume. Or you might have 2 volumes and a pressure, and then you're solving for the second pressure. Okay, that's kind of how these work. You're going to have to identify each initial pressure and volume. You'll need to figure out what you're looking for, okay, what variable you're trying to solve for, and then it's just algebra from there. Okay, so I'll show you how to do this. These are pretty simple. I think you guys are going to be fine. Okay, so here's an example. You've got this on your paper, I believe, on the next page. Given sample of gas occupies 523 milliliters at 1 atmosphere. The pressure is increased to 1.97 atmospheres while the temperature and the moles remain the same. What's the new volume of the gas? All right, here's what I like to do on these problems. I like to just label everything, okay? And I think that'll help you guys out because then you can figure out how to plug it in fairly easily into the equation. 523 milliliters, what is that? Is that a volume or is that a pressure? That's volume, right? Okay, milliliters is a measure of volume. So I'll call this my V1. Could it be V2? Doesn't really matter. I can call it whatever I want, okay? I just have to make sure that I keep it consistent. So we'll call this our V1, this 523 milliliters. 1 atmosphere, what's that? That's a pressure, right? Okay. Now, is this volume related to this pressure? This is 523 milliliters is the volume at 1 atmosphere. So if I call this V1, now I have to call this P1. Does that make sense? Okay, if I called this V2, then this would have to be P2. You just have to make sure that the right variables are related to one another. Okay? Pressure's increased to 1.97 atmospheres. Well, what's that? That's our pressure, and we've already had a pressure, so this is our P2, right? While the temperature and moles remain the same, what's the new volume of the gas? So what they're really asking us for in this one is our V2, right? That's our variable. So then when I plug that, oh, actually, I'm sorry, I didn't realize you had this P1, V1, P2, V2 thing here. And it already has, what's that? Yeah, P2, V2, yeah. It does sort of sound like R2, D2. Now I'm singing Star Wars in my head and I can't concentrate. I'm not really singing it because there's no words. Unless you count dot, 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 dot as words, but that's not really words. Sorry, I'm distracting myself here. But did I tell you that my son, that I taught him, my 1-year-old, I taught him how to go dun da da like that. So I'm like, this is perfect. He can say duh, right? Like that's one of his sounds. So let's teach him to say it 3 times in a really ominous tone. And then he can do the da 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 thing. So he goes around doing that now. And he also says, ah, nuts. He learned how to say ah, nuts. So I thought that was kind of funny. All right, anyway, back to this. Sorry, that had nothing to do with anything. So now we just write out the equation, right? So you've got P1 V1 equals P2 V2. So we just plug everything in. I don't think I have more room. Well, here, yeah, well, no. I need to see the numbers. All right. So P1 is, again, 1.00 ATM. Okay? I'm going to have to erase this stuff so that I have room. P1 times V1, okay, what did we say our V1 was? Or is? 523 milliliters. And I'm keeping the units here because I want to show you something. That's equal to our P2, which we decided was 1.97, right? Times our V2, and that's what we're trying to solve for here. You can kind of think of V2 as your X. You can think of it as your X. Maybe that's what you're solving for. So then this becomes a really simple algebra problem at this point, but it's a little bit weird as far as algebra problems go because there's units involved. But watch what happens here. I didn't mean to cross that out. I meant to underline it, and this thing is a little misaligned right now. But 1.97 atmospheres, if I divide both sides by 1.97 atmospheres, then that's going to get V2 all by itself over there, so I can solve for it. Okay, so that goes away. Now, when I divide atmospheres by atmospheres, this unit goes away also. So what unit am I left with at the end? Milliliters, which is good because we're trying to solve for volume. Okay? So then our V2 here, once you work this out, 1 times 520, why did I just punch that into a calculator? 1 times 523. Did you guys know that that's 523? Yeah, it is. Divided by 1.97. So that's giving me an answer 265.4822, whatever. How many sig figs do I need in my number here? I need 3, right? Well, this is a multiplication or division, right? There's 3 sig figs in each of my numbers. So just round your final answer to 3. So 265 milliliters is going to be my answer for V2. Now, it's always a good idea to stop at the end of these problems and just see if it makes sense, see if our answer makes sense. All right? I increased the pressure, right? So if I increase the pressure, what should happen to my volume? It should decrease, okay? It should, I pointed up because I'm thinking about this thing, but it should decrease, right? And our volume went from 523 to 265, so it did decrease. So our answer makes sense, okay? It's always a good idea to check at the end. That's not too bad, right? Pretty simple stuff? Yeah. I think you guys are going to do fine with that. Let's see what else we got here. Oh, sorry. I didn't realize this was all on here. I like writing it out myself. Okay, here's another one. Let's see, do we have time for this? Yeah, I know. Sorry. I know it's cold. So sample of oxygen gas has a volume of 150 milliliters at a pressure of 0.947 atmospheres. What will the volume of the gas be at a pressure of 1 atmosphere if the temperature remains constant? And it doesn't say this, but we're assuming that our amount of gas also stays constant, our moles of gas. Tell you what, why don't you guys take a minute, try to solve this one, okay? And then we'll talk about what the answer is. And I'll either pause the video or put on Jeopardy music, but since I don't have Jeopardy music, that was a bluff. I'm sorry. I'm just going to pause it. Whew. Okay, I don't know what's happening right now. Oh, we're recording. All right. Welcome back, everybody. So I almost deleted the video, but I think I managed not to. Otherwise, I'm just talking to myself right now. Except you guys are all here, so not really. But all right. So again, P1 V1 equals P2 V2. Okay. Just going through this one very quickly here. Our initial pressure, we can call it the 0.947 atmospheres. Again, you're just looking for your pressure units or your volume units to decide what's a pressure and what's a volume. Also, if it's at a pressure of 0.947, that's a dead giveaway that that's pressure, okay? And then a volume of 150.0 milliliters. Those two are connected to one another, okay? That is the volume at that pressure. And then what is the volume, the new volume at a pressure of 1 atmosphere? Oh, this is kind of way too much like the last one. not the same numbers, is it? Okay. Actually, this is really easy, right? Because you're dividing by 1. So you just multiply the 0.947 times 150. Gives you 142.05. You're going to know because you've got 3 sig figs in 2 of your numbers here, so you got to round this down to 3 sig figs. So it's going to be 142. Well, this is 4. That's what you asked. But since the other 2 are 3, then you'd round it. You do the lowest. Yep. 142 milliliters, right? Okay, because we're talking about volume here. And actually, the other one that's on here is exactly the same. I wish that we had picked one that you're changing to a pressure instead of to a volume, but the next one asks you to solve for volume also. You could be given 2 volumes and a pressure and asked to solve for the second pressure, but basically you're just solving for whatever you don't have in this equation, okay? So it's very simple algebra. All right, so let's go ahead and talk about Charles's law. Whoops. Charles, there's Charles, Jacques Charles. He came along a little bit later than Boyle, so I guess his hair looks better or something. I don't know. He isolated, I didn't know that, he isolated boron. And he was a balloonist. I did know that. Okay, he liked the relationship between the temperature and volume of gases because he liked hot air balloons. Not, balloonist doesn't mean like he, walked down the street with happy birthday balloons or something like that. Okay, I don't think those existed back then. But he liked hot air balloons. So what Charles found, now remember that this is like the balloon experiment that we did, okay? He found that volume and temperature are directly proportional, okay? Which means what again? If temperature goes up, what happens to volume? Volume goes up, okay? Whatever one does, so does the other. That's what directly related or directly proportional means. Now this seems a little weird maybe to you, but because they're directly proportional, they actually need to be on the top and bottom of a fraction, okay? So your equation for this one, which is already written here, V1 over, that's not right. Sorry. Should be V1 over T1 equals V2 over T2. So you need to change that equation on your sheet. Do you guys see that? It should be, no, I think that's supposed to be an equation there. Yeah, I see that they are bullets, but V1 doesn't equal T1 either. It's supposed to be all one equation. So just scratch that out, okay? Start over. V1 over T1 equals V2 over T2, okay? Sorry, I do that all the time. Yeah, I do that all the time too. And then I wake up and I'm like, what was I just typing? Yeah, that doesn't make any sense. Okay, so V1 over T1 equals V2 over T2 is your equation. So again, we already talked about this. If one temperature goes up, then the volume goes up, okay? And this is a little bit less in the realm of our experience, but according to the equation, if the volume goes down, then the temperature goes down, okay? Again, a little bit strange, but if you expand something, you can think about this in the extreme, right? So you've got a gas that's in a fairly confined area like this room, okay? Let's say that we let this gas spread out so that it's the size of the entire universe. And all that's in the universe is the gas that was in this room. Are you going to be pretty cold at that point? Probably, okay? Because remember, the temperature thing, that's how many of these particles are hitting your skin at any given time. And if they're all spread out over the entire universe, then there's not that many particles in that space, so there's not a lot of temperature there, okay? There's not a lot of heat there. So you have to kind of take it to the extreme. But if you increase the volume of something by a lot, I'm saying that wrong. Because I'm saying the exact opposite of what this is saying. You know what? Don't think about it that way. That's going to confuse you, okay? Temperature goes up, volume goes up, okay? Temperature goes down, volume goes down. Don't think about it in the other direction because it gets weird there, okay? I'm going to have to think about that one and figure it out because I just confused myself. Okay, these are just like Boyle's law problems. you got to find the 3 pieces of information out of the 4, okay? And then the 4th one you just solve for as though it were an x, okay? Now, again, this is where it becomes important. You have to use Kelvin because this equation has temperature in it, okay? These need to be Kelvin temperatures or they don't work. Now, there's a couple reasons for that, but maybe one of the practical reasons. If you ever had a temperature of 0 degrees Celsius, which that's possible, right? What's 0 degrees Celsius? What happens at 0 degrees Celsius? Water freezes, right? So it can get to 0 degrees Celsius or colder. Well, if you've got an equation that's V1 over T1 equals V2 over T2, and you try to put a 0 on the bottom of that fraction, what does your calculator tell you? It tells you don't do that. Okay? It usually says like undefined or something, or error or something, okay? You can't divide by 0, okay? So that's going to cause you problems. So let's just keep it above 0, all right? So we'll just use Kelvin temperatures for that bottom number all the time, okay? That's one of the quizzes, yeah. Because over Kelvin, conversion from Celsius to Kelvin, yeah. Well, it's also Fahrenheit to Celsius as well. And then there's some fun little sig fig things in there that you have to watch out for. Okay, so an example of this one, helium gas in a balloon. If we have time, I'll tell you about helium. Yeah, it'll be fun. Helium gas in a balloon occupies 2.5 liters at 300 Kelvin. Balloon is dipped into liquid nitrogen that is at a temperature of 80 Kelvin. What will the volume of the helium in the balloon at the lower temperature be? Okay, so we've got a balloon, and we've got 2.5 liters. Now, what is 2.5 liters? That's a volume, right? So let's call that our V1. 300 Kelvin, 300 K. That's our temperature, right? So we'll call that T1. Now, again, make sure these are related. Is this the right volume? Or am I relating the right volume and temperature together? Okay, and I am because it says specifically it's 2.5 liters at 300 Kelvin. Okay. Then the balloon is dipped into liquid nitrogen that is at a temperature of 80 Kelvin. That's our T2, right? So then they're asking for the volume. Every single one of these problems has been solving for volume so far, which is fine. This is a different kind of problem. So our V1 here, again, 2.5 liters, divided by our T1, which is 300 Kelvin, is equal to V2 over T2, which is 80 Kelvin. Now, this one's a little bit trickier. There's a couple of ways you could solve for this, okay? One way you could solve for this is by going ahead and dividing this side, the 2.5 divided by 300, see what number you get there, okay? And then multiply both sides by 80 because that'll get the volume by itself, right? So you can think about it that way kind of algebraically. But the other way you can do this is you can cross multiply and then solve, right? So you take the 2.5 times 80, and you set that equal to the 300 times V2, and then solve that way. Whichever one you're more comfortable with is fine. Doesn't matter to me. But again, this is just kind of a fairly simple algebra thing. The cross multiplication thing might be a little bit easier when your variable's on the bottom of the fraction. Might have less steps to it. So again, however you want to do it is fine. If you're struggling with that, let me know. But basically, if you're going to cross multiply, what you would ultimately end up doing here is taking 2.5 times 80 divided by 300. Okay. Is it? Oh, the 0.6666667, yeah. Well, let's just round it to 1 sig fig. How about? Because our two temperatures only have 1 sig fig, right? Everybody see that? So if we round it to 1 sig fig, we're okay because it's 0.7. Everybody okay with that number? So 0.7, what? Liters, okay? Watch your units because this one, the volume is initially in liters, then our new volume needs to be in liters as well. Okay? Everybody all right with that one? That's it? Huh? That's P1 V1 equals P2 V2, and V1 over T1 equals V2 over T2.
I just think it's all.
Yeah. I will give you the equations on the quiz. Yeah, you guys will be fine. Oh, here's the steps again, but we went over that. Okay, so there's some other practice problems on... No, there aren't. Oh yeah, there's one more practice problem on here. I'm just going to give you the worksheet on Boyle's Law and Charles' Law. Okay, I will post the answer key to this on Moodle, as usual. And there will be a quiz at the beginning of class over these two concepts. Okay? All right, that's it.